Section 7.3, solving exponential equations. So first of all, if we have two exponential expressions, they equal one another. If c to the power of x equals c to the power of y, then x equals y. This is true unless c is -1, 0, or 1. So for instance, if I had 2 to the power of 7 equals 2x, x has to be 7. Okay, so my solution is x equals 7. But if it was 1 to the power of 7 equals 1 to the power of x doesn't necessarily equal 7 because x could be 45, right? Because 1 to the power of 45 is the same as 1 to the power of 1. They're still 1. Okay? So just that little caveat there. But what we're going to try and do is to solve an exponential equation, we're going to change to the same base. So we're going to have to use some of our skills. So just some examples of changing the base of powers. 27. We always want base 3. Well, 27 is the same as 3 cubed. Okay? Another example, 9 squared. How can you write that as a base 3? Well, 9 is 3 squared, and we're squaring that because 9 squared. 3 squared squared is 3 to the 4th. We multiply those exponents. Okay, here comes a more difficult one. 27 to the power of 1/3. Well, 27 we just saw was 3 cubed. So I have 3 cubed to the power of 1/3. And then I have the cube root of 81 squared. Well, 81 is 9 times 9. And 9 is 3 squared times 3 squared. We add exponents here. We get 3 to the 4th. So 81 is 3 to the 4th. This is to the power of 2/3. That's what a cube root means. It's to the power of 1/3. Okay, we have 2 times 1/3. Okay, now we need to do some multiply. 3 cubed to the power of 1/3. 3 times 1/3 is 3 over 3, or 1. So 3 to the 1 times 3/4, 3 to the power of 4 to the power of 2/3. I multiply exponents. So I get 3 to the 8/3. Okay. Now I have 3 times 3 to the 8/3. Exponents say that we add exponents when we multiply. So let's just turn this 1 into the same denominator so we can actually add it. That's still 3 to the 1. So I have 3/3 plus 8/3, 8, 9, 10, 11, 3 to the 11/3. That would be the same thing as the cube root of 3 to the 11th. Same thing. It asked us to express it with a base 3, so this is the answer they were looking for, though. So just some exponent laws. Okay, now we're going to have to solve. So here it says we need to solve each equation. Our strategy is we're going to try and put them both to the same base. So here I have 4 to the x plus 2. And I want to rewrite 64 as 4 to the something. Well, 64, 8 times 8. Oh, it's not going to help me. 4 squared is 16. What's 16 times 16? Still not going to help me. What's 4 cubed? 4 times 4 is 16. 16 times 4 is 64. So we're doing 4 cubed. 64 is 4 cubed. So I will have to do trial and error just like you guys do sometimes. This is all to the power of x. So I have 4x plus 2 equals 4. Exponent rules, I multiply 4 times 3x. Okay, so because the bases are exactly the same, I can equate the exponents to one another. Only because those bases were the same. So I can say x plus 2 is equal to 3x. Solving for x, I'm going to subtract x from both sides. Divide both sides by 2. I get x is 2. Okay, I can check this. Is this true? So, sorry, when I divide both sides by 2 here, I should get 1. Okay, so let's check that. Does 4 to the 1 plus 2, is that the same as 64 to the power of 1? Is 4 cubed equal 64? Sure does. So there's always a check built into these as well once you get your answer. Okay, let's try another question here. 4 to the 2x equals 8 to the 2x minus 3. So solving this, I want them both to have the same base. Well, 8 can't be written as 4 to the power of something, but I do know that 4 can be written as 2 squared. So I have 2 squared to the power of 2x. 8 is 2 cubed, because 2 times 2 is 4, times another 2 is 8. So I have 2 cubed all to the power of 2x minus 3. Okay, now I am going to use my exponent laws. Here we have a power raised to a power, so we multiply. So 2 to the 4x is equal to 2. We're going to have to distribute. 2x times 3 is 6x. Negative 3 times 3 is a minus 9. Now, because both of these expressions have the same base, I can equate the exponents. So I can say 4x equals 6x minus 9. Bring the 9 over, bring the 4 over. I have 2x equals 9. Solving, I get x is equal to 9 halves. Okay, I am going to check that. X equals 9 halves. Back in my original equation, I'm going to put 9 halves in. I'm actually going to check it up here. 9 halves. Does 4 times 2, 4 to the power of 2, 9 halves, does that equal to 8 to the power of 2, 9 halves, minus 3? Well, 2 times 9 halves is just 9. Does 4 to the 9th equal, here we have 9 minus 3, 8 to the 6th. Are those equal? Well, we're going to have to use our calculator. 4 to the power of 9. So get out your calculator, 4/9. 4 to the power of 9. 262,144. Okay, and is that the same as 8 to the power of 6? 8 to the power of 6. Look at that, same thing. So we've also checked it and we know that it's true. Okay. Another way that we can solve is graphically. We can graph each side of the equation and take the x coordinate of the intersection. So I could have graphed y equals 4 to the 2x, and my second graph would be y equals 8 to the 2x minus 3. Graph both sides and take the x coordinate of the intersection. So I'll spend a second doing that. Okay, so I've graphed y equals 4 to the 2x. I have a graph there. Oops, and the second one I didn't quite graph correctly. 2x minus 3. I think I need to do a bracket. 8 to the power of 2x minus 3. Nope, still not going to let me. Okay, so I graphed these two and I had to do some crazy amount of zooming. And I saw that where these two spots intersected, and I knew they intersected because I came here and there was a nice gray spot. It was at 4.5, which is 9/2. So that was the intersection. I had to zoom quite a bit out, like I'm in 300,000 here, but there's the intersection. So sometimes using graphing is nice, and sometimes it's not as pretty to find that intersection. Okay, back to what we were doing here. So we're looking for the x-coordinate of the intersection. The next example is a little better. Compound interest. So grade 12 should have seen this before in the last math. A is the future value, P is the principal, I is the interest rate as a decimal per compounding period. So we always need to divide by the number of compounding periods. N is the number of compounding periods. Careful to multiply by the compounding periods per year. So I'll show you what that means here. So we have Keegan, he's investing $1,000 at 3.75 compounding semi-annually. So here is my principal, that's P. My interest rate, I have to first of all turn into a decimal. And because it's semi-annual, that means twice a year, we take that number and we divide by 2. Other things you might see is quarterly, so you'd have to divide by 4. You might see weekly, that would be divide by 52. It's how much per year. Now we need to model this growth. So my future value equals, just from the formula here, the principal 1 plus interest to the power of n. Principal was 1,000. 1 plus the interest, we found the interest to be 0.0375 over 2 to the number of compounding periods, but then we have to times it by 2 because it was semi-annual. So to the power of 2n. If it was quarterly, it would be 4n. Okay, so now it's asking how long will it take? We're going to solve for n if we want it to be worth $2,500. So we have an equation that is $2,500 equals 1,000, 1 plus 0.0375 over 2, all to the power of 2n. We need to solve this. There's two ways. First is trial and error by trying different numbers and putting it in, and then finally it's graphical. Okay, so I'll show you how I kind of used trial and error to help my guess. So what I did first of all is I divided by 1,000, so each side, so I got 22.5 equals, and then I did 1 plus 0.0375 divided by 2. I got a decimal for this whole part. So I got 1.01875 all to the power of 2n. I square rooted both sides because I had it raised to the power of 2. If I square rooted, I got rid of that square there. So I square rooted both sides. Okay, so I was left with the square root of 2.5 is 1.58, which is equal to, when I square root it, I just got 1.01875 to the power of n. The square rooting basically got rid of that 2 there. Okay, and then finally, I just did trial and error. I started putting numbers into the calculator. Okay, so I wanted 1.01875, and I wanted it to be 1.58. So let's just try to the power of 10. Of course, would not work. To the power of 1 to the power of 10. Oh, that might work actually. Let's go to the power of 10. Okay, 1.2, so I need more than that. So just trial and error, so I go 1.75 0.01875. Let's try doubling that to the power of 20. Still not enough. Let's try 25. 1.01875 to the power of 25. Oh, getting pretty close, so a little bit less than 25. So n is about 25. And if I had more time, I could keep trial and error until I got as close as I can. But probably the easiest way to do this question is graphically. So what I'm going to do is I'm going to actually set up both sides of the equation on a graph and find where it intersects. So that's what I did here, is I graphed 2,500 on one side and 1,000. This is plus 0.0375 divided by 2. That's what this side is. So I graphed both sides and I saw exactly where they intersected. I had to do some crazy zooming and I saw they intersected at 24.7. So that's how many years it would take in order for that to happen. Okay, so some of you from grade 12 might have some other skills like financial calculator. If you want to use those, you're more than welcome to do that. But trial and error is a good method as well. It will get you as close as you need to be for this class. Okay, so graphically or trial and error in the beginning of the lesson, of course, we learned about expressing things in the same base.